the Pharaoh's lighthouse. For nearly 2,000 years it ruled the horizon like a living god of light. It was so tall and precise that sailors said it could summon the sun itself. And yet, no one today can explain exactly how it worked, or why it stood for so long when every empire around it crumbled. What secret held its stones together? What kind of mind designed a beacon that could be seen 40 kilometers across the sea? Could one of the world's oldest machines have used principles of optics and power we still don't fully grasp? At the mouth of the Nile, where desert meets the deep, stood the city of Alexandria, the beating heart of the ancient world. Trade, mathematics and science all converged there like tides of knowledge. When the Ptolemies built the Pharos lighthouse in the 3rd century BCE, it wasn't just a tower. It seemed like a declaration that humanity could command nature. It rose over 130 meters high, second only to the Great Pyramid. Ancient historians like Strabo and Pliny wrote of its light blazing far into the night, magnified by an enormous polished mirror. But no text ever explains how that mirror was made, or aligned, or how it endured centuries of constant use. Its flame never seemed to falter, its reflection never dimmed. Centuries later, earthquakes tore through the coast, and tidal waves swallowed the tower whole. But when archaeologists began mapping the ruins in the 1990s, they found something they didn't expect. Massive precision-cut blocks, some heavier than a locomotive, still perfectly squared, resting on the seabed as if they'd been placed yesterday. Modern engineers tried to rebuild its base digitally and discovered something impossible. The foundation shouldn't have held on sand. Even the mortar resisted salt better than the concrete we use today. It was as though the builders had known secrets of stress, weight and pressure that wouldn't be rediscovered for millennia. Every modern replica has failed, collapsing under its own weight or losing its light's intensity. Did the ancients use concave mirrors of bronze, a mosaic of polished metal reflecting the sun like a beam? Some say polished limestone, others mention a rotating system. Even the fuel is a mystery, oil or resin. The deeper researchers dig, the more contradictions they find. It's as if the pharaohs belonged to another era of knowledge, a bridge between architecture and optics, designed by people who understood light in a way we no longer do. In 2022, a reconstruction team used modern stress analysis software to test a digital model. According to our calculations, the pharaohs shouldn't have lasted a single storm, yet it stood for 1,600 years. Did its builders defy physics? Or did they know a version of physics we've forgotten to ask about? Some believe it may have drawn from the same temple optics the Egyptians used to guide sunlight deep into sacred chambers. If that's true, then the pharaohs wasn't just a lighthouse. Today only fragments remain beneath the waves, columns, carved lions, shattered stone. But what they represent is bigger than any ruin. They remind us that ancient builders didn't just stack rock, they engineered wonder. And maybe, just maybe, they touched the edge of a science we're yet to scratch. If a lighthouse from centuries ago could outsmart our own age of engineering, what else could there be? The Inca rope bridges. Suspended across Andean chasms by ropes woven entirely from grass, these bridges carried armies, traders, and messengers over raging rivers. They were remade every single year, by hand, without nails, steels, or blueprints. And yet they still endured. Even now, engineers stare at them in disbelief. If a bridge made of grass could last centuries, what else have we underestimated about the minds that built them? The Inca Empire built its network not from stone but from fiber. Hundreds of kilometers of suspension bridges laced their empire together, fragile threads binding impossible terrain. They conquered the vertical world. The most famous, Huayhuachaca, still hangs near Cusco, a golden rope swinging gently in the wind. Each May, entire families gather to rebuild it exactly as their ancestors did. They harvest coya grass from the high meadows, dry it in the sun, then twist it into strands the width of a wrist. These strands are braided again and again until they form cables thick enough to bear the weight of people, llamas, even carts. 30 meters across a canyon. No metal, no machinery. Just living knowledge passed hand to hand. When modern civil engineers first studied it, they expected a relic, a crude survival from the past. What they found instead stunned them. The bridge wasn't static. It moved and breathed with the wind. Each rope flexed, absorbing tension from the others. When weight pressed down, the stress redistributed naturally, like a heartbeat finding its rhythm. It was a self-correcting structure, something modern engineering only learned to simulate centuries later. The Inca builders didn't calculate with formulas. They read the fibers with their hands. They felt the mathematics. Modern researchers tried to copy the design. They used synthetic fibers, steel anchors, and precise instruments. It should have worked better, but it didn't. The bridges failed. They twisted unnaturally, snapped too soon, or sagged like broken threads. Something vital was definitely missing. The ancient bridges only worked when every part, the ropes, the knots, the anchors, even the soil, belonged to the same natural system. It wasn't just construction, it was ecology, it was rhythm, it was a living relationship between people and their landscape. Had we become too rigid to understand what they did by instinct? How did the Inca master tension, torsion, and balance without metal tools or written plans? In 2014, a team of Peruvian engineers decided to test it. They built a replica using both traditional weaving and modern materials. Steel replaced the grass ropes. The bridge stood, but it felt wrong. It was too stiff. It didn't sway or hum. It resisted the wind instead of dancing with it. So the next year they rebuilt it the old way, fiber by fiber, braid by braid. And when they stepped onto it, the bridge sang again. It moved with the earth instead of against it. It came alive. In that moment, something became clear. The Inca weren't defying nature. They were listening to it, and sometimes the simplest designs survive because they never forgot how to move with the world. If grass could bridge the mountains, what might we rediscover if we stopped trying to outsmart the past and started learning from it? Archimedes screw. Invented in the 3rd century BCE, the Archimedes screw is so efficient that every modern attempt to improve it somehow makes it worse. How could something so simple be perfect? In ancient Greece, a young mathematician named Archimedes sat beside a river, watching farmers struggle to lift water from the canals. He studied the flow, how water followed shape. From that observation, he designed something extraordinary, a hollow cylinder with a spiral blade inside. Tilt it, turn it, and suddenly water climbs uphill. It was elegant, predictable, alive, a perfect union between geometry and motion. The Greeks used it to irrigate fields. The Romans used it to drain mines. The Egyptians used it to reclaim their deserts. Centuries later, Dutch engineers used the same design to hold back the sea. And today, 23 centuries later, you'll still find Archimedes screws working quietly in irrigation systems, wastewater plants, and hydroelectric turbines around the world. It was never replaced, only rediscovered. When modern engineers revisited the design, they assumed improvement was inevitable. They 3D modeled it, simulated flow dynamics, added seals, bearings, and polished alloys. And yet, the original, ancient version performed just as well. In some cases better. The numbers didn't lie. The efficiency curve barely changed in 2,000 years. Even with computer optimization, modern screws couldn't lift water as smoothly, or with as little turbulence, as those based on ancient dimensions. Researchers noticed another clue. Ancient screws weren't rigid like ours. They used bronze, wood, and hollow reeds, materials that expanded and contracted with moisture and temperature. As water moved through, the materials flexed, subtly balancing pressure and friction. The system regulated itself, it adapted. When modern versions were built from rigid steel, that harmony vanished. The water resisted. Energy loss increased. The smooth rhythm broke. Some fragments of old screws even showed spiral ratios that defied modern fluid equations. And yet the result was nearly flawless. In 2018, a Dutch engineering team built 2 full-scale versions, one using computer-calculated dimensions and one using reconstructed ancient methods. Their prediction was obvious. The modern one would outperform. But it didn't. The ancient-style screw, wood, bronze, no bearings, no machines, pumped more steadily at lower power. The conclusion was unsettling. Precision, it turns out, is sometimes more about harmony than control. Maybe that's what Archimedes understood. The Great Wall of China, worn, broken, weathered by centuries of wind and war, but alive. Modern engineers stare at it and ask a question that borders on heresy. Could we build it again? And if we did, could we make it last as long? The story begins more than 2,000 years ago, when Qin Shi Huang, the first emperor of a unified China, ordered a patchwork of regional fortifications to be bound into one colossal barrier. It wasn't a single wall, but a living network. Watchtowers, signal posts, ramparts, and fortresses stretching beyond the horizon. Later dynasties, Han, Ming, and others, rebuilt, expanded, and reinforced it. Each used what the land provided: rammed earth, stone, brick, reeds, and lime-bound mortar. Every section carried its region's fingerprint: desert clay in Gansu, volcanic rock in Hebei, granite in Beijing. Across landscapes of blistering heat and glacial wind, the wall became something more than a defense. Centuries later, much of that wall has faded into dust. And yet, the parts that remain continue to defy time. Sections of rammed earth, fragile-looking, unreinforced, have endured longer than modern concrete. Restoration teams armed with drones and cranes often fail to match the resilience of the ancients. Their reconstructions crumble, the originals endure. Archaeologists have found traces of ingenious machines: treadwheel cranes, rope pulleys, sledge ramps, and portable scaffolds. They also discovered something more subtle: an intuitive mastery of geotechnical balance. Builders layered earth in alternating textures, coarse and fine, compacted to create flexible strength. That let the wall breathe with the seasons, expanding and contracting without splitting. And then there's the legend of the sticky rice mortar, a mix of lime, organic fibers, and cooked rice paste. When tested in laboratories, its strength rivals modern cement. It's even resistant to water erosion, a molecular bond between starch and calcium that modern chemists only rediscovered in the 21st century. The Great Pyramid of Giza. Over 2 million limestone blocks, each carved, hauled, and placed with a precision that feels almost inhuman. Some weigh as much as 80 tons, and yet they fit together so tightly that after 4.5 millennia, not even a blade can pass between them. Every theory about how it was built eventually breaks. Every modern reconstruction fails under the weight of its own logic. Could it be that we've been asking the wrong question all along? On the Giza Plateau, the Great Pyramid of Khufu rises from the sand like a commandment from the ground. It's the last survivor of the 7 wonders of the ancient world, and the oldest by far. 4,500 years old, yet it stands almost unchanged. Its 4 sides face the cardinal directions with microscopic accuracy. Its base stones fit with mechanical precision, no mortar, no gaps. At its heart lies a maze of chambers and corridors whose purpose still sparks debate. When modern engineers scanned it with lasers, the data defied belief. Each side is nearly perfectly level, just millimeters of difference over hundreds of meters. The height-to-base ratio mirrors mathematical constants that wouldn't be defined until the modern age. So the question became, if we had to build it now, could we? We've tried. With cranes, with computer models, with billion-dollar budgets. Every time the numbers collapse, we can lift the blocks, we can cut them, but we can't organize them the way the ancients did, not with the same speed, precision, and harmony. It's the coordination that beats us, not the tools. Engineers have proposed every theory imaginable: a straight ramp stretching for miles, a spiral wrapping around the structure, a system of pulleys, sleds, and wooden rollers. Others suggest water, channels used to float stones into place. Each idea solves one problem, but creates another. The ramps would have required more stone than the pyramid itself. The spirals demand impossible space. The concrete theory doesn't fit the microscopic structure of the blocks. And then there's time. 20 years. That's the traditional estimate for construction. To meet that, tens of thousands of workers would have needed to set one massive stone every 2 minutes, day and night, for 2 decades. Perfectly. No errors, no breaks, no cranes. Even for us today, with every machine and algorithm at our disposal, that pace seems impossible. So what were they doing that we're not? In 1995, a French architect named Jean-Pierre Houdin thought he had the answer. He proposed that the pyramid was built from the inside out, using an internal ramp spiraling upward within the structure. Computer models supported it. It fit the geometry. But when teams scanned the pyramid again, the evidence wasn't conclusive. The data didn't match perfectly. The mystery still held its ground. Other researchers tried building partial replicas, testing every variable: friction, leverage, manpower, time. Each experiment failed somewhere along the line. Either the materials broke, or the logistics fell apart. The original builders worked with stone, yes, but also with insight, with an understanding of weight, rhythm, and precision that went far beyond muscle, something that feels more like symphony than construction. Maybe that's why it still stands. If the Great Pyramid was a machine of purpose, what was it built to do? Hero of Alexandria's engine. In the workshops of ancient Alexandria, a small bronze sphere began to spin, powered only by steam. It hissed, rotated, and whirled faster and faster until it seemed almost alive. The noise was strange, the motion mesmerizing. Witnesses said it looked like the breath of the gods made visible. This was the first known steam engine, invented in the 1st century CE, nearly 17 centuries before the Industrial Revolution. The man behind it was Hero of Alexandria, inventor, mathematician, and showman. He lived in a time when science and magic blurred into one, when the Library of Alexandria still pulsed with the world's knowledge, and engineers were called mechanists of the gods. Hero built the impossible for his age: automatic temple doors that opened when fire was lit, coin-operated holy water machines, fountains that ran themselves. But his most mysterious creation was a small sphere of bronze, mounted on pivots and connected to a kettle by a pipe. When water boiled below, steam filled the sphere and escaped through 2 bent nozzles. The escaping jets made it spin, endlessly, beautifully. It was a toy, a ritual, and an experiment all at once. The Aeolipile, the ball of Aeolus, god of the winds. It was, by every definition, a working jet engine. When modern engineers rebuilt Hero's design, they were stunned. With nothing more than bronze tubing and a steady flame, the device produced real, continuous rotational energy. It worked perfectly. And yet, the ancient world never used it for anything practical. Not to power mills, not to turn wheels, not to sail ships faster across the sea. It remained a temple curiosity, a machine that could have started the Industrial Revolution, admired only as a trick of faith. Why? Some say the ancients simply didn't have the materials. No iron pistons, no steel gears, no bearings to harness that motion. Others think it was cultural. In Hero's time, machines weren't meant to serve men. They served gods. In temples, doors swung open by invisible forces. Altars hissed with concealed flames. Statues moved and spoke through hidden mechanisms. To worshippers, these were like miracles, and Hero was their magician. But when you read his writings today, the tone is unmistakable. It's not mystical at all, it's mathematical. He describes pressure, siphons, air compression, and valve systems with such precision that modern engineers recognize the principles instantly. Hero wasn't guessing. He understood the mechanics of air and steam with startling depth. At the University of Thessaloniki, physicists recreated the Aeolipile using high-grade materials, perfect seals, balanced pivots, and consistent steam pressure. It spun at over 1,500 revolutions per minute, faster than some early 19th century turbines. In theory, it could have powered gears, belts, or even pumps. And so, the first engine in history spun quietly in a temple, then vanished into the silence of time. 1,700 years later, steam would roar again, and humanity would call it an invention. But the truth? We were late to our own revolution. Machu Picchu's stonework. High in the clouds of the Andes, 8,000 feet above sea level, a lost city stands as if it grew from the mountain itself. Blocks of granite, each weighing several tons, locked together with such precision that even a razor blade can't slip between them. How did the Inca, without iron, wheels, or written plans, achieve what we still struggle to explain? Machu Picchu, the hidden citadel of the Inca Empire. Built in the mid-15th century under the rule of Pachacuti, it clings to a knife-edge ridge between two peaks, overlooking the sacred valley below. Terraces that drain and breathe like living organisms, channels that divert mountain rainwater before it can erode the slopes. Temples aligned to solstices and constellations, and at the heart of it all, stone walls whose joints seem alive. To the untrained eye, it's just ancient craftsmanship. To an engineer, it's seismic science. When modern engineers ran earthquake simulations on replicas of Inca masonry, the results were stunning. Unlike our rigid concrete walls, these ancient polygonal blocks flexed and shifted, then snapped back into place. No cracking, no collapse. The walls moved with the tremors, not against them. It's an entirely different philosophy of construction, one that sees the earth not as an enemy, but as a partner. How did the Incas cut and transport stones so hard that modern tools struggle to replicate? Their quarries were miles away, across steep mountain ridges and deep valleys, and yet somehow they moved blocks weighing 20, 30, even 50 tons, without wheels, beasts of burden, or iron tools. Bronze chisels can't carve granite, and yet the Inca shaped it as if it were clay. Some say they used endless abrasion with sand and water. Others suspect heating and quenching, thermal fracturing of rock. But even these ideas fail to explain the smooth organic fits of their joints. No two stones are the same, yet together they form a wall that behaves like a single body. And that behavior is what makes them earthquake-proof. Each interlock absorbs vibration, transferring energy across multiple directions instead of shattering. In other words, they built stones that breathe with the mountain. In 2016, a Japanese engineering team recreated a small Inca wall section using modern tools, cranes, and laser cutters. Their cuts were perfect, their alignments flawless, at least on paper. But when they tested the wall under vibration, it failed first. The Inca-style replica, carved by hand with uneven joints, survived. Imperfection, it turned out, was part of the design. The Egyptian water clocks. In ancient Egypt, time wasn't ticked by gears. It was allowed to flow, drop by drop, hour by hour, through stone vessels that seemed to breathe with the rhythm of the stars. When modern scientists rebuild them, they fail. The ancient originals, carved more than 3,000 years ago, still keep better time. How is that even possible? Around 1400 BCE, when the Nile still dictated the heartbeat of Egypt, priests faced a sacred problem. How do you measure the hours of night, when the sun, their god Ra, had vanished into the underworld? Their answer was extraordinary: the clepsydra, or water clock, a single alabaster vessel, hollowed and inscribed with hour lines, constellations, and lunar markings. Water flowed from a pinhole at its base, its level dropping steadily through the night. Each level corresponded to an hour, a celestial map traced in liquid motion. The most famous of these, from the reign of Amenhotep III, still survives today in the British Museum. Its inner walls curve like the orbit of planets. Centuries later, modern engineers decided to test the legend. They rebuilt the clock using modern instruments, precise flow meters, and temperature control. But every experiment ended the same way. Their versions drifted by minutes each hour. The ancient one stayed steady. How could that be? How could a Bronze Age civilization, without formal knowledge of pressure, viscosity, or hydrodynamics, achieve greater precision than our calibrated tools? When researchers examined the clock's inner walls, they discovered the surface wasn't uniform at all. The curves changed as they descended, widening and tightening in precise, deliberate steps. Those variations compensated for changing water pressure. As the vessel emptied and the force of gravity weakened, the shape naturally corrected the flow. The result, a constant rhythm. It was a pre-programmed correction system, 3,000 years before automation. In essence, the vessel computed time as it drained. Each line, each curve, each drop was mathematics in motion. Some even suspect that small floating indicators or siphon attachments once enhanced its accuracy. If true, then these weren't just primitive containers. They were the world's first analog computers. At the University of Copenhagen, physicists built a 1.1 replica of the Amenhotep III clepsydra. Every curve was laser scanned, every dimension was recreated with modern precision tools, and yet the copy lost synchronization within hours. The original, although weathered and uneven, kept perfect pace across an entire night. It's as if the imperfections were part of the design, like a sculpted formula for flow. No mechanical clock of its time, anywhere in the world, could rival it. Stonehenge. On a windswept plain in southern Britain, a circle of stones rises from the grass, each one carved, dragged and lifted into place more than 4,000 years ago. Stonehenge rests on Salisbury Plain, a vast, rolling landscape that's seen thousands of winters. It wasn't built all at once, but in stages, evolving from simple wooden posts and earthen banks around 3000 BCE into the iconic ring of megaliths that still stands today. The sarsen stones, each weighing up to 25 tons, were dragged from the Marlborough Downs over 20 miles away. The smaller bluestones came from the Preseli Hills in Wales, more than 150 miles across rivers, valleys and ridges. To call it a monument doesn't do it justice. Centuries later, modern archaeologists tried to rebuild what they did. They carved replicas using stone hammers, rolled them on logs, dragged them with ropes. In theory, it works, but in practice, everything fights back. Friction chews through ropes, logs splinter, the ground sinks. Even with hundreds of people, raising a single upright takes days. And then there's the alignment. The stones fit into sockets only inches wider than their bases. Each lintel rests on two uprights, balanced perfectly on joints carved by hand. One mistake, and the entire structure collapses. The ancient builders didn't make that mistake. Not once. But transportation was only half the miracle. The true enigma is geometry. Stonehenge aligns to celestial events within fractions of a degree. For people without written numbers, compasses, or metal instruments, that's almost unthinkable. Today, even with cranes, laser levels, and CAD models, modern reconstructions fail to match their precision. Computer simulations show that if their bases were off by even a few inches, the ring should have collapsed long ago. But it hasn't. It's as if the builders balanced weight, vibration, and resonance in ways that defy our assumptions. The Nazca Lines. Across the barren desert plains of southern Peru, lines stretch for miles. From the ground they seem random, meaningless paths leading nowhere, but from above like vast figures. The Nazca Plateau sits within one of the driest regions on Earth. Between 500 BCE and 500 CE, the Nazca people turned this desert into a cosmic canvas. They scraped away the dark layer of oxidized rock to reveal the pale clay beneath, carving images so large they can only be seen from the air. Some lines run for nearly 10 kilometers, others form perfectly proportioned animals, hundreds of meters wide. The largest figure dwarfs entire modern stadiums. Their precision implies planning on a scale that shouldn't have been possible. When pilots first flew over the plateau in the 1920s, they couldn't believe what they saw. From the cockpit, the barren land transformed into an ancient gallery. Animals, geometric shapes, and long, ruleless straight lines that stretched far beyond the horizon. Even today, satellite mapping confirms what those first explorers felt. Modern engineers tried to trace their accuracy, and found that even with lasers, total stations, and drones, the Nazca geometry holds up frighteningly well. Archaeologists have offered many theories. Some suggest simple tools, stakes and ropes, laid out in grid patterns. Others believe they used horizon markers, measuring alignment by watching the sunrise and sunset across distant hills. But when modern teams tried to recreate large-scale designs using those same techniques, They failed to maintain accuracy beyond a few hundred meters. Their lines drifted, angles warped, the scale broke down. The Nazca, however, sustained perfect proportionality across miles on uneven terrain, with no elevation tools and no way to see the whole picture.